All right, our first video here will be over Lewis structures, and there should be a review. You should know this already from general chemistry and also from organic chemistry. But we'll go through just to refresh all this for you. So this is going to be the step that I'll go through on the next few slides. So we will start with a formula. Here we have nitrate. And first we need to figure out how many valence electrons it has. Nitrogen is from the fifth column, so it has 5 valence electrons. Oxygen is from the sixth column, and it has therefore 6 valence electrons. There's 3 of the oxygen, so we get 18 total valence electrons from the oxygens. And then we have to know how to treat the charge. A negative charge here adds an additional electron. So 5 plus 18 plus 1 gives us a total of 24 valence electrons. Then we'll want to draw our structure out like this. The least electronegative atom generally goes in the middle, so that's nitrogen goes here in the center. Also, a good rule of thumb is usually, almost always, the atom that's written first will be the central atom. So we've got that all right here. Then, for it to be a molecule or molecular ion, everything has to be tied together. And so we go in and we put bonds. There has to be at least a single bond to hold everything together. And just tying everything together uses 6 electrons. So 24 minus 6 leaves us with 18 electrons to assign. So in step 4 we do that. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now we've totally assigned all of the electrons. We don't have any more electrons to assign to the structure. But now we can move them around. And so the oxygens are totally satisfied already here in step 4. 2, 4, 6, 8. 2 from the bond and then 2 from each lone pair. So oxygen's already super happy. But the nitrogen is not. The nitrogen only has 2, 4, 6. And we're looking for an octet. We're looking for 8 electrons. And so one of these has to sacrifice. And so, for example, it could be this top oxygen here. It takes a lone pair, it brings it down, and it forms a double bond between nitrogen and oxygen. And the thing is that also that satisfies nitrogen while also keeping the oxygen happy, because whether it's down here in a bond or it's up here in a lone pair, they count the same for the nitrogen, for the oxygen. All of this is based on the octet rule. Atoms tend to gain, lose, or share electrons in molecules until they're surrounded by 8 valence electrons. Molecular compounds will share electrons. We're not talking about ionic compounds at the moment. And so, for example, water here has 2, 4, 6, 8 electrons around the oxygen, and the hydrogens each have 2. This hydrogen is bound to the oxygen. It has 2 electrons and 2 electrons here. Also, we can have multiple bonds. We'll see that on some of the slides after this. So 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for the carbon. So all 3 of the atoms meet the octet rule. Here's a good place to pause and look at this and go back and look at this later. Electrons are stabilized by bond formation. A hydrogen atom can stabilize 2 electrons in its valence shell. Carbon through fluorine can stabilize 8 electrons in its valence shell. There's always going to be 2 electrons around hydrogen, and there's always, always, always going to be 8 electrons around carbon, nitrogen, oxygen, and fluorine. So the octet rule is very strict for this set, carbon, nitrogen, oxygen, and fluorine, and then it gets a little more complicated down here. So all atoms prefer to have 8 electrons, and we'll talk about this in class. So all of them do, but there's a few that can get away with breaking the rule. So for example, atoms in the beryllium column may have 4, 6, or 8, but they prefer 8. Atoms in the boron column may have 6 or 8, but again, they prefer 8. And chemical reactivity will actually make them, if they have less than 8, be very reactive. And then we have heavy atoms. Atoms that are heavier than silicon in the P block, those may have 6, 8, 10, or 12 electrons around them. All right, so this is, we've drawn a Lewis dot structure for each fluorine atom, and each fluorine atom has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7 around each. They want to have 8 electrons, and so they form a bond. And we usually draw the bond then in as a line to show that they're connected. And now each fluorine has 1, 2, 3, 4, 5, 6, 7, 8. So this fluorine has 8, and then this fluorine also has 8. Okay, we count each bond as 2 electrons, and it counts for both fluorines. So we do a sort of double counting for the for the octet rule. Here's just a little bit of vocabulary. We have, for example, water that we talk about. Water has a central atom. That's the one that's attached to more than one atom, more than one other atom. These guys out here are terminal atoms. They're connected. The lines are bonding pairs. And the dots that are on there are lone pairs. Okay, so atoms such as carbon, nitrogen, and oxygen can end up sharing 1, 2, or 3 electron pairs to form single, double, or triple bonds. The hydrogen atom and halogens never form double or triple bonds. And so we'll run across these here in a minute. So for example, this is an alkene. It ends up needing, for all the atoms to be satisfied, it ends up needing to form a double bond between the carbons. And so now this carbon on the left, 2, 4, 6, 8, and the carbon on the right, 2, 4, 6, 8. And for carbon, we can go all the way up to a triple bond. So this triple bond here, there's 3 pairs of electrons, 1, 2, 3. And so this carbon here on the left, 2, 4, 6, 8. Carbon here on the right, 2, 4, 6, 8. So in common Lewis structures for these organic molecules, we can end up having, often having double and triple bonds. All right, let's practice a couple. So on the front slide, we looked at nitrate, which was NO3 minus. Here we're going to look at NO2 plus. Counting is going to be a little bit different. So our central atom is nitrogen. And let's figure out the number of valence electrons. Nitrogen is in the 5th column, so it has 5 valence electrons. Oxygen is in the 6th column, so 6 valence electrons times 2 of them. And then the charge here removes an electron from the total because it's a positive charge. So 5 plus 12 is 17, minus 1 gives us a total number of valence electrons that's 16. Okay, we're going to follow the same procedure, put the nitrogen in the middle, and tether everything together. That requires 4 of the electrons just to make sure everything's stuck together. Satisfy the terminal atoms first. 2, 4, 6, 8, 10, 12. Okay, so that's 12 to satisfy those oxygens. And now we've used the entire pot of electrons. 4 plus 12 is 16. But not everybody's happy. The nitrogen here at the moment only has 2 4 electrons around it. And so the central atom, in order for it to have an octet, it has to form a double bond to both sides here. Now all the atoms are happy. The oxygen 2, 4, 6, 8. The other oxygen 2, 4, 6, 8. And the nitrogen 2, 4, 6, 8. And all of these have to total up, of course, to 16 electrons. Let's do one more. We can also have something, this beast here has 2 central atoms, but the first part of it is similar. So we have to figure out the total number of valence electrons. Each carbon brings in 4, and each fluorine brings in 7. This gives us a total of 36 valence electrons. And so first, again, we tether everything together. The carbons, we're going to tether here together, and we're going to attach 2 fluorines to each one of the carbons. That uses 10 of the total electrons. We always want to go around and satisfy the terminal atoms first. That uses 24 of the electrons. And so, that uses 34 total of the electrons. 10 plus 24 gives me 34 total electrons getting used up. And Then to make the central atoms have an octet, the best way to do this here is to form a second bond between the two carbons. You might think at first, if you only were to focus, say, on the left carbon here, you might want to put a lone pair there, and then this carbon would be happy, but this one would still only have 6 valence electrons. So if you put a lone pair on the right one instead, the right one would be satisfied, but not the left one. And so however you want to get to it, you end up coming up with a double bond.